Welcome to the DIY Honda Garage channel. The Diagnostic Trouble Code, or DTC P16E3, is associated with the PGM-FI, or Programmed Fuel Injection, indicating a communication error with the battery sensor through the local interconnect network, LIN. This error signifies a disruption in the communication between the vehicle's engine control unit, ECU, and the battery sensor, crucial for maintaining proper engine management and battery functionality. The battery sensor itself is typically located near the battery, often integrated into the battery cables, where it monitors battery voltage and current to relay accurate information to the vehicle's PCM, or powertrain control module. The PGM-FI system uses this data to optimize performance and efficiency, making troubleshooting this DTC critical for ensuring smooth operation. In essence, the failure of communication can lead to symptoms that affect engine performance, fuel economy, and overall vehicle functionality. The battery sensor plays a vital role in monitoring the voltage and current levels of the battery. It is generally mounted close to the battery terminals, allowing it to accurately measure the battery's status. Communication occurs over the local interconnect network, or LIN, which is a serial network protocol used for communication in automotive electronic devices. The failure of this communication can prevent the PCM from receiving accurate battery data, which in turn can lead to engine performance issues and reduced fuel efficiency. If the battery sensor fails or has loose connections, it could cause the system to operate with incorrect or no data, leading to the DTC P16E3 being triggered. It's essential to address this error promptly to mitigate any potential issues impacting the vehicle's functionality. There are several potential causes for the P16E3 DTC. Firstly, loose battery terminals can disrupt the communication between the battery sensor and the PCM, leading to intermittent data transmission issues. Secondly, a faulty battery sensor may fail to correctly monitor battery parameters, which could cause the PCM to trigger a communication error. Another possibility is a shorted LIN circuit, which might occur due to damaged wiring or connectors that cause unwanted connections. Additionally, an open wire within the LIN can also prevent the necessary communication signals from being transmitted, triggering the DTC. Each of these potential causes must be addressed to ensure proper functionality and reliability of the vehicle's electrical and engine management systems. The DTC P16E3 can manifest itself through several symptoms that drivers may notice. Primarily, the check engine light will illuminate on the dashboard, indicating a diagnostic trouble code has been recorded. Drivers may also experience poor engine performance, which could include sluggish acceleration or rough idling. Additionally, there might be a noticeable reduction in fuel efficiency, as the engine control system may not be effectively optimizing fuel delivery without accurate battery data. Furthermore, intermittent electrical issues may arise, such as problems with starting the vehicle or odd behaviors from other electrical components. Overall, these symptoms may lead to more significant concerns if left unaddressed. The first troubleshooting step for the DTC P16E3 involves preparing the vehicle for diagnostic testing. Start by turning the ignition switch to the on position, which powers up the vehicle's electrical systems without starting the engine. Next, use the HDS, or Honda Diagnostic System, to clear any existing DTCs stored in the vehicle's memory. After clearing the codes, wait for approximately 10 seconds before checking again for any pending or confirmed DTCs. This process helps to establish a clear baseline by ensuring all temporary faults are cleared. If DTC P16E3 is still present, it indicates that the communication error remains, necessitating further investigation into the possible causes of this issue. In this second step, the focus is to conduct a thorough check for any pending or confirmed DTCs, utilizing the HDS once again. Identifying if DTC P16E3 is indicated is essential, since it could correlate with the problems experienced with the battery sensor. If P16E3 appears, you will need to continue the troubleshooting process outlined in the diagnostics. Conversely, if P16E3 is not present, this might suggest that the system is functioning properly at the moment, directing you to investigate possible poor connections or loose terminals on critical components, including the alternator, battery sensor, and PCM. Recognizing these indications is crucial for a systematic approach to diagnosing the underlying issues. For step 3 of the troubleshooting process, you'll begin by turning the ignition switch to the lock position to ensure the vehicle's electrical systems are deactivated to prevent any accidental shorting. Once the ignition is off, carefully disconnect the battery sensor 2P connector, which is critical as it allows access to the communication line involving the LIN circuit. Following this, use a multimeter to check for continuity between two specified test points. One at the battery sensor connector terminal number 2, and another at the body ground. This checks whether the LIN communication line is intact. If continuity exists, it confirms that the circuit is not the source of the problem, leading you to the next troubleshooting step. If not, it signifies a potential problem in the wires or connections. The fourth step involves further checking the integrity of the LIN line by initially jumping the SCS line with the HDS. This action ensures that the diagnostic system is ready for continuous checks. Continue checking for continuity between the battery sensor 2P connector terminal number 2 and body ground. To narrow down the fault, disconnect connectors one at a time. First, the alternator 1P connector, and then the PCM connector B, which has 49 pins. Observing whether the continuity disappears after the disconnection of a specific connector provides crucial diagnostic information. If continuity is interrupted when disconnecting one of these components, it indicates a fault in that specific part, and appropriate replacement or repair should follow. In this fifth step, you begin by reconnecting the previously disconnected battery sensor 2P connector. To assess potential issues further, disconnect the alternator 1P connector. Next, you will measure continuity between the alternator 1P connector terminal number 1 and body ground. This procedure is crucial as it identifies whether there is a break or issue in the LIN communication line coming from the alternator. If continuity is present, you may consider replacing the battery sensor, as this suggests the sensor is likely faulty and unable to communicate correctly with the PCM. Should continuity fail, the process leads you to subsequent checks to fully diagnose the problem. Step 6 requires repeating the initial step of jumping the SCS line with the HDS, preparing for continuity checks on a more extensive level. Disconnect both the battery sensor 2P connector and the 49-pin PCM connector before proceeding. You will then check for continuity between the specified points on the automotive communication line. Specifically, check between PCM connector B terminal number 16 and battery sensor 2P connector terminal number 2. Confirming the integrity of this LIN communication wire is essential, as a successful continuity test indicates no open circuits in this line. If continuity is not found, this infers there is an open wire between the battery sensor and the PCM, warranting further investigation and correction. The seventh step entails ensuring that the ignition switch is turned to the lock position for safety before conducting any fuse checks. Locate and inspect fuse number A14, rated at 10 amps, situated within the under-hood fuse/relay box. This fuse is integral to the battery sensor's functionality, and verifying its condition could eliminate it as a potential cause for the DTC P16E3. By testing the fuse for continuity, you determine whether it is operational and intact. If the fuse is good, you can proceed to the next step. However, if the fuse is blown, it indicating a short circuit situation in the +B horn wire, necessitating repairs and replacing the fuse before further diagnostics. During the 8th step, you will once again disconnect the battery sensor 2P connector to ensure accurate voltage measurements. With the connector removed, measure the voltage between the specified test points while the ignition is still in the lock position. This checks for battery voltage at the battery sensor connection terminal number 1, ensuring that the wire leading to the battery sensor maintains a proper supply. If you find battery voltage present, it confirms that the +B horn wire is functional, allowing you to move forward to the next troubleshooting step. If voltage is absent, it suggests an open circuit between the battery sensor and the number A14 fuse in the underhood fuse relay box. This would require correcting any identified faults and restoring voltage supply. In the 9th and final troubleshooting step, repeat the procedure of jumping the SCS line with the HDS to ensure readiness for checks on the LIN wire. After this preparation, disconnect the PCM connector B, followed by checking for continuity between the specified test points on the LIN communication line, while keeping the battery sensor 2P connector disconnected. Verifying continuity confirms whether the LIN wire connecting the PCM to the battery sensor is intact. If continuity is present, the issue likely lies within the battery sensor itself, which should be replaced. Conversely, if continuity is absent, an open circuit existing between the battery sensor and the PCM needs to be repaired before proceeding. The final repair verification process is crucial to ensure that all issues have been addressed. Start by turning the ignition switch to the lock position before reconnecting all connectors to their appropriate locations, ensuring no connections are left loose or improperly seated. After everything is securely connected, switch the ignition to the on position to power the vehicle's systems. Utilize the HDS to check for any outstanding or new DTCs. Confirming that DTC P16E3 is no longer indicated suggests successful repair completion. If any fault codes persist, especially related to previous issues, further investigation into underlying problems may be necessary to restore full functionality. Preventive maintenance is essential to prolong the life of the vehicle's components and avoid issues like DTC P16E3 in the future. Regular inspections of electrical connectors, especially around the battery and PCM, help to ensure that they remain secure and free of corrosion or damage. Additionally, monitoring the health of the battery can prevent deterioration and disconnects caused by weakness or failure. Periodic software updates for the PCM are similarly important, as manufacturers often provide updates that optimize performance and address any known issues. Implementing these maintenance strategies helps in ensuring the vehicle runs efficiently and recognizes any issues immediately. In conclusion, understanding the implications of DTC P16E3 is crucial for maintaining the Honda CRV's performance. The battery sensor's role in effective communication with the PCM is paramount, as it directly impacts engine management and overall vehicle functionality. Following a systematic approach through the outlined troubleshooting steps is essential to accurately diagnose and correct the issue. Awareness of potential symptoms and causes fosters a proactive approach in addressing any possible relation to this DTC. Lastly, Emphasizing preventive maintenance will aid in reducing the occurrence of related problems, ensuring smooth and reliable operation of the vehicle over time. Please like and subscribe to the channel. See you next time.